Rosa.
Okay.
All right.
So I want to start where Mike stopped. So Mike, on Tuesday, was telling us the application, right? Like, because so far we have defined these symmetric functions and that evaluate at characters of the symmetric group. But I guess the most beautiful thing to me is the combinatorics that has been introduced. So Mike told us, like, you know, that there is a unified combinatorio descriptions for the following. There are 4 products, and one is H mu, the regular homogeneous symmetric functions with S tilde lambda. Then there is this one, like H1, H2 tilde multiplied just as polynomials, mu1, mu2, tilde times S lambda. And then there is the S tilde mu1, S tilde mu2, S tilde mu L, S tilde lambda. So all these products, repeated products, H tilde mu and S tilde lambda. So these two are different because like here, the H mu's are multiplicative, but these ones are no longer multiplicative, so they will be different. And this one right here contains the Peery rule. Peery rule, right? Because it allows us to multiply like a one row times any one, right? Like, and that's the Peery rule for when you're doing products of symmetric functions. So Mike also told us the following. He said that when we looked at the coefficients, right? This one right here is mu L tilde is lambda. This tilde. This is when we put less than or equal, we mean the coefficient. And I'll do an example in a second. I just want to state what Mike had said at the end of his lecture on Tuesday. Is lambda. And this is a smaller, the coefficient, right? So if you look at a particular coefficient of some S tilde gamma in here, like the coefficient in here will be smaller than the coefficient with which it occurs here. That's like the short, when we do like, a sure positivity, for example, this would be S tilde, right? So in this one, the coefficient, so if you compare the coefficient of the same S gamma, right, is going to occur as smallest here, next biggest here, and next biggest here. And then he also said that we have the following comparisons: S tilde mu, S tilde lambda, H tilde mu, S tilde lambda, and this is smaller than S mu S lambda, where this is the sure function. So there are 2 problems that are outstanding in combinatorics. Well, in the combinatorial representation theory of the symmetric group, right? One is the restriction problem, and this one would be contained in here. So if one was able to obtain a combinatorial rule for this would solve the restriction problem. And if you, well, and this one right here, right? Like if you look at this one, right? Well, this would be reduced Kronecker. Right? Like you could give a combinatorial interpretation for reduced Kronecker, and we are actually kind of, working like this is how these things are related. Oh, and sorry, I forgot like the inequalities. So anyways, so the combinatorial objects that our work has introduced, which I think is the value of one of the valuable things that we have obtained, combinatorial objects that we are using to represent everything. So Mike showed you how they were coming about, right, in his talk. Multiset tableau. And I'm going to, so in our multiset tableau, like we will have an alphabet that, and we are going to choose this order. Like in this, I mean, like in this work, in a lot of different cases, you can choose different orders. The only thing, things will change, right? So, and I'm going to do it via an example. Like, so here, it kind of explain to you what it is. If you want to go read it, sometimes, you know, like a formal definition basically takes away from the simplicity of the objects. So, so let's make observations about what these things are. So first, notice that the boxes are filled with multisets. That's why they are called multiset tableau, filled with multisets. And the letters are coming, so these are our letters, and these are the order of the letters, right? The letters are coming from this alphabet, so they are filled with multiset, and at most 1 bar entry. And there is a meaning for this, you know, why there will be at most 1 entry when one is doing the product. So it is also a column strict. And it is column strict with respect to a reverse lexicographic order, reverse lex order, which means that if you put, if you look at two words, right, you start looking at the end, right, and compare the last two end entries. If they are equal, you move to the next one, right? And you compare the next entry to the next one. And this is smaller than the one in this order, right? So that's how you do that comparison, right? Then one thing that will play a role is the shape. It has a skew shape always. You always have empty boxes, like, you know, kind of length, the second row, right? Like that. So the shape is always of T is always going to be equal to some gamma, right? Where you are removing. So in this case, it's 3, right? The number of boxes that you remove, because the second row is length 3, right? And in our case, this shape is 4, 3, 3, 3. You just read the lengths of the rows and you skew by the second row of the diagram, right? And then you have to worry about a content, right? Like in all the tableaus that we've talked about, and when you're doing algebraic combinatorics, more in terms of symmetric functions, you're always worried when you have a tableau, what is in the tableau, right? And there is a content, and you're going to keep track of it in two ways. There is a bar, and there is an unbar, right? And the bar here, right? So you record how many one bars, how many 2 bars, etc. And you get 6, 3, 2, right? So let's look 6, right? Like how you count the number of bars. You see what you have 1, 2, 3, 4, 5, 6. Oh, you're right. So maybe let's do it carefully, right? Maybe with coloring. 1, 2, 3, right? 4, 5, 6, 7. So 7. I think it's because I changed it because I wanted layers to be, okay, 7, 3, 2. Yes. You can count that there are only 2 bars, right? 1, 2, 3, right? And there are 2, 1, 2, okay? And then you count the unbar entries, right? And then So how many bar entry? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And then there are 4 unbar twos, unbar twos. So you keep track of that. And we are going to call the set M, T, gamma, lambda, mu in general, right? Because we are going to have, this is going to keep these are the bars, the bar content, and this is the unbar content. And this is going to be the set of all this tableau of shape. And we'll say gamma, where gamma is actually the shape of remove the first row, right? So this is kind of like shape of T, remove the first row. This one, okay? Okay, so now I want to tell you about, so when you're doing the Littlewood-Richardson rule, there is this, the way that you read the entries, right? Like, so I'm going to show you how to do the reading entry here. Like, so how do you read? You have to extract a word, right? So there is a lattice condition, and remember the lattice condition in general, right? Is actually when you have a word, right? You always at any point in the word you want more i's than I plus ones as you read the word. And I'm assuming here that you're familiar. Mike talked about on Tuesday about the two rules for computing the Littlewood-Richardson. And one is in terms of extracting a reading word and checking that it is lattice. So let me show you how you would do it here with a picture, right? So to read the lattice condition, what you do is you ignore the bars, right? And you look at all the possible multisets that you can get of only the unbar. So you could get the empty multiset, which is smaller in order than the multiset that contains one, right? You see this is the blue boxes contain the multiset one. Then you look at the next bigger one that occurs, and it's the multiset that contains 1, 1. Then you look at the next one that occurs, and it's the multiset that contains 2. And then the multiset that contains 1, 2. And then I color-coded here the boxes that contain each of the multisets. And what you're going to do now is you go to all the boxes that do not contain unbar entries, right? Like these two. And you're going to read in the same way as you read when you're doing the Littlewood-Richardson rule, like, from right to left, so you read them from here to here and from here to here, like that, right? So when you read this one, you would read 1 bar and 2 bars. So you will extract from here 1 bar, 2 bar, right? Then, so this is kind of corresponding to this green word, yep. And then you're going to have a blue word that is going to be concatenated. And so you read from the bottom. So the first thing that you encounter is the 3 bar, the 1 bar, 1 bar, 2 bar. And this becomes kind of like the blue word, right? But they are concatenated like that. So then you do the orange one, and then you will you only read the bar entries, right? You don't read anything else. So 1 bar, 1 bar, and you ignore this one because it doesn't have bar entries. Then you go to the next, and you have the pink ones, right? And you have 2 bar, 1 bar, and then you go to the green ones, which 3 bar, 1 bar. So this is the green part. So choose this one, and then the pink one. So you extract a word that looks like this, right? And then you check that it is lattice, right? Check if lattice, right? And in this case, it's lattice, and that's why there was a typo before, because the first example I had chosen was not lattice, but this is lattice, because at any point, right, there is always more 1 bars than 2 bars, and there is always more or equal 3 bars than 2 bars, right? So kind of that regular definition, and here I put the order of the colors in which you would read them, right? So basically you're kind of deciding a way in which to read it. So, so in this case, it checks out that this is lattice, right? Anyways, so here are the combinatorial interpretations, right? That we got from Mike's proofs on just by reinterpreting things. So I'm going to create a table, right? So here is the product. So we have H mu S tilde lambda. Sorry. Then here we had 4 products, remember, H1, H mu 1 tilde up to H mu L tilde S lambda tilde. Here we had H mu tilde S lambda tilde. And here we had S mu 1 tilde up to S mu L S lambda tilde. So these were the 4 products. And here we have the coefficient, right, of S gamma tilde, right? So what is the coefficient in each? So in this one is the number of T in this multiset, this set that I defined, lambda mu, such that T is lattice, right? Like all the terms defined. And I'll do an example in a second. Here, so here, maybe I kind of color it, that it is kind of like, this is what this number is counting, right? It's the coefficient of that in this product. This counts the number of T in multiset tableau gamma lambda mu, right? Such that T is lattice. But in addition, you N, right? You have that the entries are sets. So no repetitions allowed in the boxes. Right. Then the next one, right? So for this one, this is going to be the number, the same T in the same set, right? Such that T is lattice. And the sets allowed, so it's kind of sets again, but you are only allowed are, you could have a bar entry and a non-bar entry, or you could have just a bar entry or just an unbar entry. So at most one of each. That's kind of like the rule here. And then the last one, which is the one that, you know, kind of contains the Peery rule, right? Like the one that we would eventually like, empty gamma lambda mu, right? Such that T is lattice. And the entries and it has set entries, like the same as this one, is kind of a subset of this, has set entries and no sets of size 1 are allowed in first row. of n minus gamma, comma, gamma. Okay, so these are and it shows you like the containment that Mike showed. So I want to do a table, right, to show you like an example, right? So here I kind of drew them ahead because I have trouble doing straight lines. So here is our example. So we take in this example mu to be equals to 2, 1, and lambda to be equals to 2, 2, right? So I'm basically looking, I will write the products on the other side. So, but this implies that the numbers that I will enter in the tableau, I'm gonna have a 1, 1, 2 coming from this, yeah? And I will have a 1 bar, 1 bar, 2 bar, 2 bar, and these are coming. So these ones are giving me these ones, right? And these ones right here, oh, well, let's use this one. These ones are giving me these ones, okay? So let's do the example, right? So I wrote the first one because they kind of, and I try to do like a different example that is on the paper, but it's kind of things get really big or they are very trivial, right? So I guess we chose well in the paper to the example. So I'm going to do this example that is in the paper. Okay, so this one would be H1. So if you multiply H to 1, multiplied by S tilde to 2, right? And you are looking here for the coefficient of S tilde 4, right? So that's the, so in this case, there are 8 tableaus, so that the coefficient is 8, right? Then you look at the next one. Okay. And the next product was H tilde 2, H tilde 1, right? Separate S tilde to 2. So the condition was, remember, that you do not allow repetitions in the boxes. And so by looking at it, notice that this one is the only one that has a repetition. It has a 1, 1, right? All the other ones satisfy the condition, so you can kind of just kind of cut, right? Sorry, copy, and then you paste. And you can definitely see this containing there, right? And this is the coefficient is gonna be 7, right? Then the next one, okay. In the next one, I wanted H tilde to 1 times S tilde to 2, right? And if we go back and look at what the conditions are, we only want these types of entries, right? So we so it's going to be still sets. So we want to look at which ones would get eliminated, right? And this one would get eliminated. And I look at all the other tableau, and they all have those types of entries. So in this case, all of these ones satisfy that condition. So the coefficient is 6. And then finally, the last one is tilde 2, is tilde 1, is tilde 2, 2, right? Or I think we were putting them, the order doesn't matter because it's commutative. So in this case, we wanted set entry. So I go back to this one where there were set entries, right? But I'm not allowing now. So I kind of, let me kind of mark the ones that I cannot allow. I don't allow this one and I don't allow this one. And so because these ones, remember the condition that you do not allow sets of size 1 on the first row, right? So then it is just this right here. Paste. And in this case, the coefficient turns out to be 5. So this is the example like of what Mike did last time, right? So he presented like, you know, how the sausage is made, and I'm just giving you the sausage. So it's kind of like, it feels pretty good kind of to see how everything fits together, right? Anyways, so which I feel, I mean, like there were combinatorial interpretations, but they were all like all over the place. So what we are trying to do is kind of like unifying them all and giving like a framework in which you can actually compute any product whatsoever, right? So, so now I want to go back, right? And I thought that I would state our main theorem. In the paper, right? Like because I'm trying to summarize and bring everything together, tie it up back, right? And our main theorem basically said that there exists a non-homogeneous or inhomogeneous basis is still the lambda, right, of symmetric functions characterized by any of the following. And we, in our previous 5 lectures, we have basically, you know, kind of kept telling you this. Mostly Mike presented, maybe, hold on a second, I moved this one. This is for later. So you have lambda 1, right? Then this basis is unique, right? In the sense that it evaluates to the characters of the symmetric group, right? Which is kind of what we've been saying all along. These are the irreducible characters of the symmetric group. Evaluated at some, so then these right here are eigenvalues, right? Of a permutation matrix of cycle type mu, which is this mu right here, okay? The second one, right, it told me that if W lambda is a polynomial representation of GLN, right? Oh, maybe I think the letter that I used in my tag, my first tag was B lambda, is irreducible, right? Then it's this basis is also characterized to be the unique one that satisfies this condition. Sorry, I went and looked at the paper, but the one that I used B lambdas in my first tag. If you restrict from GLN, right, to SN, viewed as symmetric group, viewed right as permutation matrices, then this decomposes as mu. These are the irreducible representations of the symmetric group, right? And then the multiplicities are lambda mu, and these numbers right here, right, are known as the restriction coefficients, which are unknown, right? Then, right, so if this happens, then S lambda, the sure function, right, when you write it, the change of basis coefficients from the lambdas to the S tildes, right, are going to be these numbers again, right? So the same restriction coefficients occurs for both, right? Like, and this completely characterizes the S lambdas. Then the third part of our theorem in our papers is that if these bases are also characterized by 2 conditions, S1R equals to S tilde 1R plus S tilde 1R minus 1, so which is equivalent the same thing as saying that that S tilde 1R is equals to the sum of -1 to the I E R minus I. So I'm basically telling you what so it's kind of like I'm telling you what the initial value is, kind of giving this is for R here is greater or equal to 0, right? So I'm giving you the initial values because if you don't specify an initial value, there are more than one that can satisfy this condition, which, if you remember, was the question that I wanted in my first. I wanted to come up with a basis of symmetric functions such that when you multiply them with a regular product, right, of polynomials, you obtain the reduced Kronecker coefficients, right? These are the reduced Kronecker coefficients. And what this is saying, what this part of this theorem is saying, is that there are several, right? But if you actually require this, right, then this is going to completely determine, like, as a basis that satisfies this condition and satisfies this condition or has this initial value is going to give us a unique. And why does this choice make sense, right? So maybe I say, why does it make sense to choose this as the initial value? Is that this is the character of the exterior power, R exterior power, Cn, right? Which is an irreducible representation of GLN, right? So, and when you decompose it, if you restrict this, right? If you restrict this to Sn, right? Is from GLN, right? It's an irreducible representation of GLN, then you actually do get the right thing. You get S 1R, right? That example. Maybe I shouldn't write it like this because you have a first long row, right? So you will get N minus R 1R, right? That exam is N plus 1 minus R 1 to the R minus 1. Like, so it decomposes in the right way. So I had prepared kind of like a little proof to show you, how the uniqueness comes, but I'm running a bit slow on time. So if we have time, I can return or answer questions if you are curious. So that's some pages. But what I want to show you is, so in my first talk, I talked to you about characters, symmetric functions. As characters of GLN. Right? And what I want to do is I want to kind of create a table, right? So they kind of, and here you have the representation, and here we have the character at element with eigenvalues x1 up to xn, right? So these are representations of GLN, okay? And so the irreducible, right, representation B lambda has character S lambda, which is the Schur function. So this is from the first lecture. If you look at the symmetric tensors, lambda 1 Cn, tensor sim lambda L Cn, right? Then this is going to have the characters are the homogeneous symmetric functions. If you look at the lambda 1 Cn tensor lambda Cn, you get the elementary symmetric functions. If you take the tensor product of two irreducible representations, right, P mu, then this corresponds to the product S lambda S mu, right, which we know is the coefficients are the Littlewood-Richardson coefficients. When you write them in the short functions back in the irreducible basis for in this case, right? If you look at V tensor K as a representation of GLN, right? This turns out to have character H1 to the K, right? And if you write it in terms of the short functions, right? This is F lambda, or maybe I put it in upper script, F lambda. F lambda is nu, where this one is the number of a standard Young tableau, right, of shape lambda. And if you look at it, V tensor K as a representation of GLN cross SK, right? This was P mu, right? X1. So I told you this the first during the first lecture, and this mu is the cycle type of an element of SK, right? Because you're now are evaluating it at an element, right? At a pair of, one is a matrix and one is a permutation. This is the cycle type, right? And these are the eigenvalues of the matrix, right? And you get the power symmetric functions, okay? So now let's compare like this table and try to create a similar table of what we have told you this week, right? So now for the symmetric functions as characters of Sn, right, of the symmetric group, when it's viewed as contained in the general linear group. So in this case, so we can create the same table. And here I have a representation of Sn, right? And here I'm going to have the character at element of cycle type mu. Cycle type. So if I take the irreducible representation, well, that was still the lambda bar, right? Like, so you remove the first row, and then here we had the psi mu. Then if you do M lambda, which are the permutation modules, which are isomorphic to the trivial representation induced from a Young subgroup, S lambda L to Sn, right? Then this is the H tilde lambda bar, right? Evaluated at this psi mu, right? And I'm going to start putting the evaluations, but if you can also do a tensor products now based on like these ones, right? In analogy with general linear group, if you do this n minus lambda L, right? Then the characters turns out to be S tilde lambda 1, which are the products that we were trying to multiply. So basically we have a combinatorial interpretation for this, for the coefficients that occur here, which are given by the rules that we told you, lambda L, right? So the like multiplicative, right? Which is not equal to this, right? These are not multiplicative bases. It's just a new basis of symmetric functions because you obtain, this is a new basis. And if you do M n minus lambda 1, and you take tensor products of these, then you're going to get H1, H lambda 1 tilde, H lambda L tilde, like that. So, and this is a new basis of symmetric functions again. And this is what we were after, right? S lambda is what we are still after, right? Oh, sorry, I forgot the big row. I'm gonna write it n minus lambda, size of lambda, n minus size of mu, right? And then this is S lambda tilde, S mu tilde. So I'm not putting the evaluations, but they are all evaluated, right? this is the sum of G bar, lambda mu nu, right? Is tilde nu, which are the reduced Kronecker coefficients. And finally, because I want to kind of show you, so here, right, Cn tensor K, right, as a representation of Sn Pk, right? Like, remember? And I told you that this right here was the partition algebra from the first day. Kind of. Then this one, the character still turns out to be the same, right? Like it's just P mu, right? Sorry, P gamma, not mu, and P gamma, psi mu, right? And this gamma, right? This is some kind of conjugacy class representative of partition algebra. And it can be any partition gamma less than or equal to K. Yeah, that goes from C, it can be from 0 up to K. Like, so you get any possible, that's what that is a partition of. So I'm looking at the time, and what I want to show you, right, is like that there is a Murnaghan-Nakayama rule. For computing, for expanding this. So we would want to write, right? Because this, what this is saying, right, that if I write it as a so this, right, I told you that's how the whole path, the whole project began, that this will actually turn out to be, right, characters of the partition algebra, right? Like if you write it, evaluated at some elements, some representative elements, right? Here some lambda, and then you had S tilde lambda here, evaluated at eigenvalue, at the eigenvalues, right? So the coefficients, when you write the P mu's in terms of the S tildes, turn out to be characters of the partition algebra, right? And a Murnaghan-Nakayama rule will allow us to expand this in this, because so this, the classical case, so maybe quickly, right? Classical case. In the classical case, right? If you want to write, you had that if you write P mu, right, as a linear combination of Schur functions, S lambda, right? And this follows from Schur-Weil duality, right? So this one is lambda, and you have a mu here, right? And you do a sum over all lambda, right? And these were the irreducible characters of the symmetric group. And how can you obtain this, right? There is a rule, there is a theorem, right, in combinatorics that tells me that if I multiply a pk times s mu, right? Did I do it correctly? Yeah, this is gonna be the sum, or an s lambda, but I need a lambda. So of all mu, or lambda containing mu, -1 to the height of lambda slash mu minus 1 is lambda, right? This is the classical Murnaghan-Nakayama rule. And by, kind of like, if you start here with the empty diagram, right? And you can multiply like all for any partition, right? It would give you an expression, and the expression of the coefficients are actually the characters of the symmetric group. And the rule, right? So when you're kind of, just to remind you, right? So here, if for instance, I have P4 is to 2, for example, right? so the way that you do it is that you start with a diagram like your 4, right? Because it has to contain, and you have to add a rim hook, right? So this, the condition here is that lambda mu is a rim hook, or that's kind of one name. There are other names, and you add it. And what this means is that you have to add like a piece, right? And the piece that you add has to be connected, like, but it has to be connected by edges, right? Like you can have like this, or you could have this, or you could have. So in the, and these are the rim hooks that you're adding, right? So the theorem that we have, like we gave a symmetric function, but this is the characters of the partition algebra were studied by Halverson. He has a very nice article talking about it, but we, Mike and I gave the symmetric function. It says that pk is lambda tilde is equal to, so wait, not nu, where nu is less than or equal to k plus lambda. Then you have here, the coefficient turns out to be a sum of things. D divides k, right? Like for all divisors of k, you're going to sum overall alpha, and I'll tell you in a second what those are. And you have the same heights in lambda mu, like alpha, sorry. But I'll show you in an example, -1 plus height of lambda alpha mu, sorry, nu alpha, like that. So this is the coefficient, and here you have S tilde nu. The sum is overall nu. So -1. So maybe I put a -2 here to indicate that there is a minus from each one. So I'll show you like the combinatorial, because it kind of looks more complicated than what it says, right? So maybe I have done a bigger example, but I'm gonna do, so what is this? So what is this alpha right here are partitions. So I need to explain the partitions such that lambda alpha and nu alpha are rim hooks. So both, right? Like the lambda is coming from here, right? And you have this nu, so you have two partitions that are going on, right? What does this notation mean, right? Like before I only had a slash, right? But this means that you add a long row, long first row, right? To lambda, right? So let's do a small example, right? So let's say I want to compute P2 times P lambda, right? I want, so example. Suppose I want to compute a P of 2, 1, right? Well, this is equals to P2 times P1, right? Because it's multiplicative. So if I do P1, right? So what, just kind of a very simple example, right? So you start with lambda, right? And lambda in this case is empty, right? So this is equals to S empty, like tilde. There is no lambda, like, so then what I do, right, to construct it, I add a first long row to lambda, which is empty, right? And what the rule is telling me to do is I can reinterpret this and say, well, remove a rim hook from lambda of length 1, because the only divisor in this case is 1. Divisor of k is 1 here, right? K is equal to 1. So there is only one divisor. So you remove the k, and the height is 1 in this case, right? of the rim hook that you remove, and then you add it in all possible ways. That's what the rule says. And then like this. So then this implies that P1 is equals to S tilde empty plus S tilde 1. So you look at the shapes, because here the height is again 1, height is again 1. So if you put these numbers right here, right, you just get 1 as coefficients. So now let's say I want to multiply. So I want to multiply P2 times this, right? If I want to do the product, now that I have these ones, this is the same way that you would do it. So now this is equals to P2 S tilde empty plus P2 S tilde 1, right? And if you do that, right, now K is equal to 2, right? So you have two cases. You have D equal to 1, right? And D equal to 2, right? Those are the possible divisors. So here you have this, and you remove a box like that, right? Of D equal to 1, right? And then you do the same process as we did before. You can add it here, or you can add it here, okay? So that does it, because I'm computing this product right now. So right here, K equals to 2, so I have P2 is tilde empty, right? So then the other case, right, I can remove a rim hook of length 2 from here, right? And then I can add a rim hook to whatever is left, right, in all possible ways. So I can add it here, or I can add a rim hook that looks like this, or I can add a rim hook that looks like this, right? And then I have to record here the height is equal to 2, right? All the other ones are just height 1, right? So then, so this is, if I multiply this P2 times this, right? So this is going to give me here, P2 S tilde empty gives me S tilde 2, right? Sorry, empty. From here, this one and this one, right? And then I have plus S2. Then I have S tilde 1. Then I have minus S tilde 1, 1 plus S tilde 2. So basically, you remove the first row, right? And then just copy the shapes that you get. Like that's what the theorem is telling me to do. And if you compute P2 S tilde 1, which I'll leave it as an exercise, what you will get is, I did it on papers. I should have 3 S tilde empty plus S tilde 1 plus S tilde 2 plus S tilde 1, 1 plus S tilde 2, 3 plus S tilde 1, 1, 1. And I think that's it, because when I compute P2 1, like I hope I didn't make a mistake. I get, oh. Sorry, I was miscopying. This is just 1. Okay, so what I end up getting, right, is this plus 4 S tilde 1 plus 2 S tilde 2 plus S3 S tilde minus S tilde 1, 1, 1. And I want to show you that what this computes, right? So this is the character table of the partition algebra in 3. And what this computes, right, in the same way as it computed for the symmetric group, what you're computing are these columns, right? These are the entries that correspond to each, like 3, like 4, 2, right? 0, the 1, 1 doesn't occur. It actually cancel out because it occurred here. but it occurs in the second one with a negative. It appears with positive in one and negative, so it cancels out. And then this is basically what you're computing. So, which gives us the connection to to the partition algebra, how the representation theory is playing a role, right? So, so maybe I will end up, you know, I kind of had like prepared like something about a change of basis and kind of what we know and what we don't know. But I guess, you know, we're running out of time. So what I want to show you is the following, right? That in the classical case, right, in classical representation theory of SN and GLN, right, we basically have right here all representations of all symmetric groups. And this is a ring. And the operation here, right, you take a representation of any symmetric group, right? And you take another representation of any other symmetric group. And the operation is induction. And you're inducting, right, take from the group S lambda S mu, right? Like that, the sizes of it to S lambda plus mu, right? What we saw the first day is the Schur-Weil duality, right? Which some people call this is a functor, and it's called the Schur functor, right? Here, right, you have polynomial representations of GLN, right? And the operation is tensor, right? Like here, the operation is induction, right? Here, the operation is tensor, right? You tensor representations, right? And here, right, symmetric functions. The product is just regular product of polynomials. And here, right, so this is just, people called it the universal character, right? So it basically gives us the characters, right, when you evaluate them at eigenvalues. And here, this is the Frobenius map. And we have combinatorics structures. Here, the tableau. So the combinatorics here that helps us understand all of this are tableau filled with numbers, with sets of size 1, right? And or multisets of size 1. It also RSK, right, helps us understand if you take BI1 tensor, right, tensor BIK, you can interpret this as a word, right? And when you insert it, you get PQ, right? And these ones correspond to semi-standard Young tableau, which are what index a basis for representations of GLN, and you get a standard Young tableau, which index representations of SK, right? So you have this connection right here. And then the third is the Littlewood-Richardson rule. Right? So now in our restricted world, right, which is what we are trying to kind of convince you that it's kind of like the restricted picture, right? So you will have exactly the same, but now here, right, you will have all representations of partition algebras. And the product will, again, be induction. So you can induce products of partition algebra. And here you're going from P lambda cross P mu, right, to P lambda plus mu, right? And I wrote a paper that describes, you know, these in connections to partition algebras with Bowman and Derbyshire, right? That explains how this works. Then here, like you have Jones and Martin, right? People who work with a partition algebra basically connected it here to representations of the symmetric group Sn, right? Here n very big for us, right? But it doesn't have to be, right? And here the product is tensor again, right? So the product stays the same, tensor, right? Induction. And here we have, right, symmetric functions. And what we have done with Mike, right, it is say that the same correspondence works, symmetric functions, right, with regular products, same product, right? And the combinatorics, right, that we are telling you works, right, is that instead of filling the tableau with numbers as such in here, right, we are filling the tableau are filled with multisets, right? And we have also tried to define an RSK, right, that gives the correspondence. You know, kind of here the O is me and C is Mike, Colmenarejo, Saliola, and Schilling, right? We have given you a Pieri rule, right? For doing the product, right? And instead of saying the end, I would say to be continued, because we believed that we are just starting kind of, and that hopefully we will be able to obtain more, right? You know, kind of in the story of how this generalizes, kind of things becomes very, you see, the existence of multisets, right? Is that things are becoming equivalent, and it's very hard to see where things came from, right? If you only have that result. So anyways, I had prepared like another 5 pages to kind of create the analogy, but I think we want to go sleep, right, Anna?
No, I cannot. I still have to go to work actually after this. So
anyways, okay. So that's you know, what I wanted to tell you.
thank you so much, Rosa, and thank you so much, Mike. This is such a great lecture series.
Well,
It's
and thank you for
wonderful.
organizing, you know, kind of.
Any questions in the audience? I actually have some questions. So like, I feel like this is like a generalization or kind of like a variant, I say, of like the symmetric functions, right? Like a bunch of, because you're looking at these characters and then you have like your S to the H to the P to the. So how about anything more like kind of, does that work in the world of like Hall Littlewood, or even like modify the McDonald or do something similar, or like Jacobi Trudy formula with all these like H tutor, what would that be? And like, does that make sense?
Oh, I was hoping that Mike would jump in. I thought it was well, you know, so okay, so this is well, I didn't tell you, you know, all the change of bases that were not known, right? And the ones that were known, like to kind of so we know how to write H mu, right, in terms of the tildes, right? Because those were just multiset field tableau, right? Column strict multiset tableau. We knew how to write mu in terms of the tildes, right? But what you're saying is in terms of Hall Littlewood, like how would you write a Hall Littlewood in terms of the tildes, right? So now you would get polynomials, right? And we don't really know.
I see.
Like there will be polynomials, not necessarily positive, right? Because the P when you set the t to 0, you get either monomial or shear functions. I don't remember exactly. And when you set the t equal to 1, you get. So when you specialize it, right, the p's. So basically, you will want to write the p's in terms of shear functions, right? And when you specialize it at the other, you will get the monomials. Oh, so shear functions in terms of S tildes, or you would get monomials in terms of S tildes, right? Because the piece is specializing like that. But those are, we don't know how to do those, right? So there is kind of like, so there is a lot more work to be. I wanted to kind of, present you with a, it's too bad that I ran out of time, like to just show you what the coefficients are, because what the coefficients are, if you actually try to understand them, what they are being is kind of like a version of the classical, but now you're kind of having multi-set entries or set entries, right? But you're having exactly like, like the EMU, I don't know if you remember, they were multi-set tableau, right? And you were allowed, when you write EMU in terms of the S tildes, so maybe I write, because when we wrote the EMU, right, in terms of the S tildes, and for a while I was kind of puzzled by this, right? But now I'm not, right? So these numbers right here, right, you were getting some multi-set field tableau, right? Or set field tableau. So maybe I say set field. They were set field, right? Tableau. And like one of the conditions is that the odd sets, kind of, it was row strict on row strict on odd sets, right? And it was column strict on even sets, right? And if you write EMU in terms of the regular shear functions, right? I'm gonna put tilde here, and you put lambda mu equally. These ones right here are sets of size 1, if you like. So filled with numbers, right? So the sets are all size 1, right? And it is row strict. So do you see? So this is one way that you could think, well, these are kind of like Cosca numbers, like, kind of you, kind of like, because you can obtain it by applying the omega involution, right? But for instance, if you want to write E to 1, right? The way that I learn is you do 1, 1, right? And you don't want to put them, so you have 2 1s and you have a 2, right? So maybe I say 2 here so that it's more interesting, right? So you have 2 2s. And the condition is that there cannot be 2 1s in the same row or 2 2s in the same, right? So you could put 2 2, right? Or you could have 1 1 2 2, or you could have 1 1 2 2, right? So, but now the sets are size 1, right? So you could think that this is kind of some generalization, like, because now you're allowed to have sets of any size, right? So if you actually study all these identities that Mike and I have obtained, you can see that they are actually very similar to like the classical, right? The only difference is that you're feeling and understanding how like the even sets and the odd sets are, kind of relating to each other and what the restrictions are, right? That you're having. I guess that's what might lead to like a better understanding and probably, finding a combinatorial rule. So what we are trying to pitch in our talks are that if a combinatorial rule exists for all these problems, right, you will be able to probably give it in terms of this set field tableau.
I see. Okay. Or I was also wondering, like, if you have this like S to the E to the or P to the H tutor and every of this tutor, and then I was like, would there be also like Hall Littlewood, but it's a variant of that, like just a tutor version, or like a McDonald with a tutor version or something like that. But I don't even know
Yeah,
if that makes sense. But
yeah, because okay, so because I was thinking about your question about the um the Jacobi-Truri identity, right? So
right,
how does the
yeah,
Jacobi-Truri comes in, right? And the
right,
Jacobi-Truri comes in when you want to write is lambda, right? In terms of the H muse, right?
mm-hmm, yeah,
And so now you would want to write a tilde lambda, right?
mm-hmm,
But perhaps not in turn. We know how to. Well, we don't. We know how to write H mu in terms of the tildes, but so perhaps you see when I talked about here, like when I was talking about this, so there are these new bases that we have introduced that we haven't explored almost at all, right? And these are
mm-hmm,
multiplicative. So these are kind of
right,
new bases that we introduce in the products paper. So all these new bases that are arising, and these ones are going to be multiplicative, right?
mm-hmm,
So I don't know if there is a rule, like in terms of either writing that in terms of these spaces, like that doesn't have a name yet,
mm-hmm,
right? And perhaps this is the right thing to take. Perhaps this one, right? Like for
mm-hmm.
like a
I see.
Jacobi-Truri, right? Does that
Yeah,
make sense?
yeah, yeah, yeah,
Because,
yeah.
but yeah, I don't know. So there is a lot to explore, right? Like
Yeah.
because I mean we really don't know, kind of how these bases are kind of interacting with each other. We have combinatorial interpretations, right, of how to
Mm-hmm.
write this, right, from
Right.
what Mike presented and what is above, because in all this, right, you could always take this to be as empty, right? Yeah.
Mm-hmm.
And what you will be getting on this side is just tableau, set tableau, right? With those restrictions, you just don't have bars, right?
Mm-hmm. Yeah.
But you can actually do here from all these rules, you can obtain actually the combinatorial like interpretations when you write. But now if you want to go backwards, right? So here, like, from this one, you can get, kind of a products of H tildes, right? With
Mm-hmm.
indexed by 1 rows, right? In terms of the S tildes, right? And
Mm-hmm.
from here, you would get products of the S tildes kind of like in terms of S lambda or S gamma tildes, right? Like if you put this to be empty and they would just be like set tableau, right?
Mm-hmm. Yeah.
So then, are these the right thing, right? Like to look at it, kind of if you want to write this and try to obtain some Jacobi-Truri light identity, like,
Mm-hmm.
I don't know.
Yeah, but it's very interesting, and I think that there may be something there.
Yeah. So, I mean, it's kind of, it's kind of like unexplored.
Yeah.
Like,
Do we have a minute? I what kind
Yeah.
of your question where you kind of touch on Hall Littlewood.
Right.
The answer is completely unexplored.
Uh,
I do have ideas though, in the sense that the way I classically look at Hall Littlewood and McDonald is they come from creation operators.
right.
And so you can put these into context of, you could ask, are there creation operators for these bases? And then can you queify those creation operators? And
Right.
then you might be able to get at some of these questions you're asking. Again, completely unexplored, really cool questions. There are too many directions to go, right?
Mm-hmm. Yeah, yeah.
which is
I do
exciting.
understand. Yeah,
As
that's
Adriano would
great.
say, it's really exciting. Like,
Is there a multi-set version of McDonald fillings?
Exactly.
right.
Yeah, that would be like very interesting to look at all these direction. All right, I think like we are running out of time. So thank you so much for Mike and Rosa again. So we'll be back next week with Eric talking about a new series of topics. So stay tuned. I'm going to email everybody. All right, thank you. Have a
Okay,
nice
bye.
day.
Thank you, Anna. Bye.
Bye.